Hi, welcome to Minds of Pint Einstein, the science show. My name is Marcus Chown. I'm a science writer. I'm the author of books like Quantum Theory Cannot Hurt You, The Ascent of Gravity, and my latest breakthrough. It's my enormous pleasure today to have with me Dame Jocelyn Bell Burnell. Famously, as a graduate student at Cambridge in 1967, she discovered pulsars, the relics of supernova explosions, where a star is compacted into a volume about the mass of about the size of Mount Everest, and these objects actually spin at maybe up to 700 times or more a second, which is absolutely mind-blowing. Famously, also, Jocelyn was overlooked for the Nobel Prize, which went to her supervisor, and there have now been 3 Nobel Prizes for pulsars, none of which have gone to the discoverer. Jocelyn is also the first person I've ever interviewed whose discovery is featured on a banknote, the Bank of Ulster, Northern Ireland £50 note. But she is one of my scientific heroes, not simply because of her groundbreaking discovery, but because of her enormous determination in the face of a lot of adversity. And because of her generosity, in 2018, she won a £2.3 million breakthrough prize, and she's used that money to help disadvantaged minorities, women, refugees, ethnic minorities to do physics. So it's my great pleasure to welcome Jocelyn to the program. Welcome, Jocelyn.
Thank you very much, Marcus, and thank you for that generous introduction.
Which I stumbled over quite a bit, but you told me off air you've just been in Ghana, and incredibly, you told me that it was actually colder in Ghana than England. What were you doing in Ghana?
Yes, it was cooler in Ghana, but that's maybe because the temperature in England has been exceptional. In Ghana and in several other African countries, there's part of the African Institute of Mathematical Studies, abbreviated to AIMS, set up by Neil Turek, who's now a professor in Edinburgh. And it's to raise the educational standard in maths and maths-related subjects in those African countries. So I met a number of young Africans from various countries who were all studying fairly advanced mathematics and apparently enjoying it.
And the idea is, I remember Turek talking about finding an African Einstein. You know, why wouldn't there be somebody of the caliber of Einstein in a continent as big as Africa?
And they have a lot of young people.
Absolutely.
So the next Einstein is probably African, but it's maybe still a teenager or in their early 20s.
We'll get back to that at the end of the program, but can we start with the discovery of pulsars, which is something that you've probably recounted a million times, but let's assume that most people who are listening haven't heard about it. So you arrived at Cambridge in 1965 and you helped build a very strange radio telescope. What was it like? Can you describe it? And what was it designed to do?
It looked a bit like an agricultural frame because the most obvious thing were lots and lots of wooden posts. The wooden posts are actually to keep the bare metal antennae up out of the wet grass. It rains even in Cambridge. Covered about 4 acres, 57 tennis courts, and worked at quite a low radio frequency. There's antennae that run horizontally. And in the picture up now, you can see some antennae. You can see a pair of wires like a tram line looping down and ultimately going into a cable. The whole thing was huge, 4 acres plus. That's 57 tennis courts, if that helps.
Yeah.
And it's large because it's working at quite a low frequency. The wavelength was close to 4 meters. So most of the antennae were several meters long.
And it was built to study interplanetary scintillation. What is that?
Yeah, it was built to find quasars using interplanetary scintillation.
Okay.
Quasar is a very compact object, and as the beams of radio waves come from it to the Earth, they pass through interstellar space and the space between the sun and the planets. And in particular, the space between the sun and the planets is not empty, because the sun is exuding a plasma, charged particles, electrons and protons. And these things can affect the transmission of the radio wave. And if in any sense they're grouped into clouds, they can cause the apparent signal from the distant object to fluctuate up and down. To scintillate is the word.
So this is the same as twinkling in our atmosphere. So turbulence in our atmosphere causes the image of a star to flip backwards and forwards, and we see that as twinkling.
Yes.
And in interplanetary space, there is the as you say, the plasma of the solar wind, and that has variations as well, which will cause an image of a distant quasar to fluctuate and twinkle in the same way. So really, but big things, I think, isn't the thing that big things like the moon, obviously they are affected in this way, but they only kind of wave around the edges and we don't notice. So it's only the very small things that twinkle. So that was why this was sensitive to quasars, which are super compact.
And they only twinkle at radio wavelengths, so you have to use radio telescopes.
Right.
You won't see it with an optical telescope. You won't see the twinkling with an optical telescope.
Right. And was one of the key features of this telescope that it could actually discern very changes over very small timescales of only a few seconds or something like that?
Yeah, because the twinkling's quite rapid.
Yeah.
So each of our data accumulations, our integration time was 1/10 of a second. So we got 10 different measurements every second.
Of the brightness of the radio sources you were looking at.
So as we could see the signal going up and down.
And the telescope started working in 1967, and it produced a lot of data in the form of a pen trace, a pen recorder on a roll of paper, didn't it?
That's right.
And I believe there was a lot of it, which you had to sift through. And on one day, I think it was the 28th of November 1967, you noticed something unusual. What was that?
Yeah, there was over 3 miles of this paper that I analysed, rolls and rolls and rolls of it. By the 27th of November, we were actually pinning it down. Earlier than that, I was being extremely thorough, very, very careful. And I noticed that there was occasionally a signal that I didn't understand, couldn't classify. And then I twigged that it was coming from the same constellation all the time. It was keeping its place amongst the stars. So it's some kind of star doing something that I don't understand. And I discussed it with my supervisor, and he rightly said, look, it's only occupying 1/4 inch on your charts. You can't see what it is.
Right, we put it up now. This is the trace. So at the very top,
that's right.
Is the up and down fluctuation of this radio source, and then at the bottom, on the bottom line, you seem to have actually put a mark, a tick for every dip in the brightness, and it's amazingly regular.
Yeah, actually, those bottom ticks are 1 second marks.
Oh, they're 1 second marks.
The whole stretch is about 20 seconds, and the pulse separation is about 1 1/3 seconds. Not every pulse is there; it's a bit near the threshold of detection, but when there's a pulse, it's on beat.
So you told your supervisor, Tony Hewish, about this. What was his reaction?
Well, he said, nothing astronomical behaves like that. It must be radio interference. And you get quite a lot of radio interference, taxi radios and badly suppressed cars and aircraft altimeters and things. But none of that gives a string of pulses like this that keeps its place amongst the stars.
You persevered and you found 2 more.
3 more.
3 more.
I found the first 4. Finding the second one was really good, because that showed my supervisor that I wasn't stupid or bonkers or anything like that. And finding 3 and 4 were a bonus.
Right. And initially they were classified as LGMs, for little green men, weren't they?
Well, that was my informal classification, yes.
Did you seriously ever think that this was a message from extraterrestrials?
Not by the time we had numbers 2, 3, and 4. No way. If there had only been one and forever only one,
Yeah.
you might have suspected little green men, yes.
Yeah.
But there aren't lots all deciding at the same time to signal to this curious planet Earth.
And what were the periods of the others? If the first one was 1.3 seconds, what were the other three?
The second one was 1.25. The third one was really exciting because it had a period of 1/4 of a second. So it was going blip, 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 blip 4 times a second. Really fast.
So tell me about the announcement. I mean, were you involved?
We wrote a paper which went to Nature, which is perhaps the top British scientific journal. And a few days before that paper came out, Tony, my thesis advisor, gave a talk announcing the discovery in Cambridge, gave it a very titillating title, and everybody came. And you could see the jaws drop as he went through the talk.
And nobody really knew what it was. But then eventually Tommy Gold suggested that pulsars were neutron stars. Is that right?
No, Fred Hoyle had beaten him to it.
Fred Hoyle, okay.
Fred Hoyle came to that colloquium. And when Tony finished speaking, Fred was the first to comment. And he started to saying in his best Yorkshire accent, "This is the first time I've heard of these things. I don't think they're white dwarfs. I think they're neutron stars."
Now, neutron stars had been predicted by Zwicky in Fritz Zwicky and Walter Baade in the 1930s. I mean, almost immediately, the same year that they discovered supernovae, they'd actually thought that they were the energy to power the supernova came from the collapse of a star to a neutron star.
Mm. But they had to wait a long time before we got proof of that.
Yeah. So tell me about a neutron star.
It's about 10 miles across. It weighs the same as the sun, so it's incredibly dense. In fact, most of it is so dense it's beyond the physics that we're familiar with. So there's a lot of interesting research going on very dense matter and how it behaves. They spin very rapidly. They've got a very strong magnetic field. And just like on the Earth, magnetic north is not at the true spin north. Similarly with the pulsar. And the beam seems to come out of the magnetic north and then sweeps around the sky as the star spins. And you see a pulse each time, pulse, 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 pulse.
Kind of like an interstellar lighthouse.
Yeah. And indeed, when we start traveling through space in spaceships, those things would be our lighthouses, our beacons.
Yeah. And so really, I mean, matter, the matter that we're all made of is made of atoms, and in a kind of, I suppose we can think of atoms as like a planetary system with a nucleus at the center, like a sun, and electrons orbiting like planets. But that doesn't really tell you how empty atoms are, does it? So if you squeeze all the empty space out of all the atoms, you end up with this neutron star material. I think isn't it a sugar cube size volume would weigh as much as the human race, something like that?
Something like that, yes. Certainly a lot, almost beyond human imagination.
And but the surface gravity will be what, something like 10 billion G?
Surface gravity is huge. Obviously, if you were on one of these, your skeleton wouldn't stand up to it. You'd collapse.
Mm. Yeah, and we are very fortunate they do have these beams of radio waves which they emit. Otherwise we would, presumably these are very small and very faint objects that wouldn't be visible in any other way.
That's right. But equally, if time comes when we travel through the galaxy in spaceships, those things will be our lighthouses, our navigation beacons.
And now, is it true they are still better timekeepers than our best atomic clocks?
Yes, they're incredibly reliable. I mean, they are gradually slowing, running out of steam, but it's very, very gradual.
Now, if we fast forward to 1974, your supervisor, Tony Hewish, got the Nobel Prize, but you didn't. He died last year, unfortunately, sadly. But I did see a video on the internet of him comparing the discovery of pulsars to Columbus's discovery of America, and saying that the person who first spotted land shouldn't be the one that was remembered, but the person who actually, set up the expedition, Columbus. But that isn't really very fair, is it? Because you weren't just the first person to spot them. It was your tenacity that actually resulted in a discovery.
That's certainly true, yes. It is always very difficult assigning credit for discoveries. And the Nobel Committee are limited in how many people can share the prize. So they do have problems there, I will admit, yes.
Yeah. So, I mean, that was an unfair comparison, I think. But I understand. I mean, I think that you were the student, but you played a big role in actually creating that telescope, and as I say, in being tenacious in tracking down that signal. I mean, wasn't there a precedent? There was Rudolf Mossbauer in Germany who also used his supervisor's equipment, but because his supervisor had tenure, he put Mossbauer's name first on the paper, and he won a Nobel Prize.
Mm.
So maybe you should have got it. I understand that Fred. Well, you just mentioned Fred Hoyle,
Yeah,
and I think he always said that he was surprised to find a week after the announcement that a student had actually made a discovery.
Mm.
And then when the prize was awarded, as you know, he wrote a letter to the Times criticizing the Nobel Committee for not giving you the prize. What did you think about that?
well, Fred never got on very well with the radio astronomers in Cambridge. And I think this was one of the issues he used to criticize them, beat them up about.
Yeah.
The Nobel Prize Committee has a hell of a job because there's always too many people and not enough Nobel Prizes, so to speak. So, yeah, students can get overlooked, I'm afraid. Can happen.
Yeah. And then, of course, when the prize, when later, of course, Fred Hoyle was overlooked for the prize. Willie Fowler, his colleague, got it for cosmic nucleosynthesis, the building of atoms inside stars and inside the Big Bang. And I think he was told that he didn't get the prize because he criticized the committee before. So, I mean, do you know anything about that, or what do you think
No,
about that?
I
Nothing.
hadn't heard that one before.
Yeah. I mean,
I'm not actually sure that the Nobel Committee ever gives feedback. So I doubt the story, to be honest, Marcus.
yeah, well, he said that to me, but unofficially. I mean, he actually said that when he didn't get the prize, he was very miserable for 3 days and really quite cross. But after 3 days, he thought, well, history will recall that I did do what I did and will give me the credit. And I don't know, is that the way you feel about pulsars?
I've done very well out of not getting Nobel Prizes for pulsars, because if you don't get a Nobel Prize, you get every other prize that moves. If you do get a Nobel Prize, nobody gives you anything else because they can't match the Nobel. So I've had more fun, more prizes.
Okay. I mean, I've never met a professional astronomer who did not say that you were unfairly treated. That is the general opinion, that you really should have got that prize. But yeah, so it's all water under the bridge now. Does that help that most professional astronomers do think that you should have got that prize?
Well, as I say, it does mean I've got virtually every other prize that moves. So
I think you said something about that you're in good company being overlooked. I mean, who else do you think was overlooked?
I didn't have specific people being overlooked. I was just thinking how few scientists had the Nobel Prize and what a large number don't.
Yeah, but I mean, particularly women. I'm thinking of people like Henrietta Leavitt, who's, the discovery that Cepheid variables behaving the way they did has allowed us to measure the size of the universe. I think of Cecilia Payne Gaboshkin, probably wrote the most important astrophysics PhD of the 20th century and figured out what most of the universe was made of, most of the non-dark matter universe was made of, and didn't get the prize. So you are in really good company.
Yeah.
I'm struck by the fact that the two endpoints of the evolution of massive stars, pulsars and black holes, were both discovered by women, or black holes were co-discovered by Louise Webster.
Yeah. Yes.
Did you know Louise?
I knew of her. I didn't really know her well. No.
Because I mean, sadly, she died at 49. I think she was the first person in Australia to have a liver transplant. But again, I mean, there's another. I talked about 3 Nobel Prizes going for pulsars, and none going to you. But now there've been 4 Nobel Prizes for black holes, and none has gone to the discoverer, or the surviving one, which is Paul Murdy. So maybe history is repeating itself.
But on the other hand, there's been a Nobel Prize to a woman just last year, Andrea Gates.
Yeah, for black holes. Yeah.
Hole at the center of our galaxy.
Yeah. But,
lovely piece of work, that.
Yes. So that is actually measuring the orbits of
stars.
A few stars right in the center of the galaxy, where we've got a 4.3 million solar mass black hole.
And it's wonderful to see Kepler's laws demonstrated by those stars orbiting the black hole. If there are any science teachers watching, it's worth getting hold of the video, because it's a wonderful demonstration. The star comes along, and as it gets the black hole, it goes zip and round slowly, and zip.
So speeds up as it gets very close, and then slows down as it's further away.
That's right. Yes. Yeah.
Which is Kepler's, I don't know, what Kepler's second law is that?
Oh, never mind. Kepler's laws.
First law is things travel in ellipses, so I think that might be Kepler's second law. No, fantastic. So can we talk about your life and the problems you face? Because what happened at your school? You grew up in Northern Ireland. Your father was an architect who designed the Armagh Planetarium. Is that true?
Yes.
Yeah. And is that how you got interested in astronomy?
No, I was already interested by then. In fact, I'd found the first pulsar, went home that Christmas, went with Dad to Armagh Planetarium to see how it was getting on. And Patrick Moore was there as the first director, presenter. And he just got a starry sky up. And I surreptitiously looked to see where the constellation of Vulpecula was, because that's where the first pulsar was. And it's very crowded. It's in the galactic plane. The chances of making an optical identification were zilch, I knew as soon as I'd seen that planetarium sky.
And so, yeah, so your dad was designed that planetarium, but when you were at school, I think you had problems even doing science, didn't you?
Yeah, when I moved into secondary school, this was in Northern Ireland, girls did domestic science, boys did science, because everybody knew that girls were only going to get married and be stay-at-home wives and mothers. So we needed to know how to cook and sew, whereas the boy needed to learn crafts so as they could get a job as a metal worker or a woodworker or what have you.
Yeah. So you did. So, but your parents had to fight for you to even be included in science classes.
And the local doctor also had a daughter in the class, and he was phoning the head teacher also. So the class ended up with 3 girls and all the boys. And I think we were the first girls that teacher had ever taught. He clearly thought we were dynamite, and he made us sit right up against his desk, right at the front, with all the boys behind, flanking.
And then when you went to the University of Glasgow, tell me what happened when you used to go into lectures.
Well, at that time in Glasgow, it was the, quote, tradition that when a woman entered the lecture theatre, all the guys whistled, stamped, catcalled, banged the desks, and everything was wooden, so they could make a great old noise. And the women used to gather outside the lecture theatre, go in as a group. But in the final 2 years of physics, I was the only female in a class of 50. So I had to face that on my own. And it was important that I did not blush or otherwise look embarrassed, because they'd only make more noise. And I learned to control my blushing. I think I've lost the technique, but you can control your blushing. So I walked in absolutely poker-faced and took a seat.
This is absolutely appalling. I mean, it sounds absolutely terrible. I mean, what about the staff members that allowed this to happen? Did you think about that? I mean, how come they allowed it to happen?
Some of them looked as if they wished they could join in, but at least they didn't.
Wow. And then you wanted, after your first degree, you I think you worked a bit at Jodrell, but then you were told that you couldn't work at Jodrell, and there was a reason for that. Jodrell Bank, which is near Manchester, the big 210-foot radio telescope.
Yeah, I worked one summer at Jodrell Bank, which was a superb experience, except they hadn't expected any women to apply to be summer students. And there was a feeling, well, more than a feeling, the other grad students were really clear that Jodrell would never take a woman as a grad student. Apparently in the past there had been one, and she and the male grad student put the dormitory to a use for which it wasn't intended.
Right.
He bragged. Sir Bernard got to hear about it and said, no more women.
Wow. And Sir Bernard Lovell was one of the pioneers of radio astronomy in Britain after the Second World War. He worked on radar, and then he was a really important figure, wasn't he?
And he got that great big radio telescope built, which they then used to track the first Sputnik.
They put it on the map. They'd only just built it about a year before, hadn't they?
Something like that.
Yeah. So you couldn't go to Jodrell, but you ended up at Cambridge. Mm-hmm. How did you feel at Cambridge? Because you were a woman, you're from Northern Ireland. Did you feel an outsider?
Yeah, well, up till then I'd been in Northern Ireland, Yorkshire, Glasgow, all quite far north, mountainous part of the world, and end up in the deep south of England in this dead, flat place. Very few women, full of young men, full of self-confidence, absolutely assured of their own brilliance, absolutely assured of their own right to be in Cambridge. If he'd been a bit older, Boris would have fitted that model beautifully. He's a bit younger than me. And I thought, my God, they've made a mistake admitting me. They're going to discover their mistake and they're going to throw me out. So my strategy is to work my very hardest so that when they throw me out, I'll know I haven't wasted the opportunity. I've done my best and I just wasn't bright enough. So I worked very, very hard and took note of details like funny little signals in my chart recordings.
So the adversity, all the difficulties you'd faced, they played a role in your actual discovery because they made you super determined to prove yourself.
That's called imposter syndrome. And we now recognize it quite widely. So if there's anybody else watching this who thinks they suffer from imposter syndrome, my technique of working really hard and doing your best, do that, you'll probably win through.
Yeah. So, it comes back to my point. You made that discovery because you worked much harder than anyone else. And you weren't simply the person who saw land first on Columbus's expedition. There was more to it than that.
And actually, pulsars had been sort of discovered several times previously, but nobody had believed. Oh. So one of the features of having discovered pulsars is every so often somebody comes up to me and says, I nearly discovered pulsars, and tells me the story.
And presumably that was because no one in their wildest dreams could imagine a star that spun on its axis every second.
Well, two of the best examples were women reporting it. And in that case, it was the Crab Nebula, which beats 4 times a second, which is really fast. And those 2 women weren't believed or weren't paid attention to.
Is that because women who make discoveries are generally not believed, or that their papers are not taken as seriously as men?
One of them was a member of the public looking through a telescope on an open observatory night and said, that star's flashing.
And was it? I mean, could you really see a visible object flashing in the center of the Crab Nebula?
So it goes 30 times a second. Yeah. Some people can.
Wow.
We know this because in Canada, the mains power supply used to be at that frequency. And it tends to be young women who've got the best acuity in this respect.
Wow.
Yeah.
Now, so you made your discovery at Cambridge and then it was announced. How did the media treat you?
Oh, pretty shockingly, because I was a young woman, wasn't I? So they'd interviewed Tony and I together, and they'd asked Tony about the astrophysical significance of this discovery. And then they turned to me for what they called the human interest. So how many boyfriends did I have? What was the color of my hair? Would I describe it as brunette or blonde? Who other colors were allowed? How tall was I? What were my bust, waist, and hip measurements? How many boyfriends did I have? Etc., etc.
This is actually terrible. Do you think things have improved since then? Thank goodness.
Yes, they're better. There's probably room for more improvement yet, but they're a good deal better.
I mean, the last person I interviewed was Laura Massini, who is a cosmologist in America, Albanian, and she was saying that she finds that the things that she presents are not accepted as easily as things that are presented by male colleagues. So there's still a reluctance to accept the results of women. Mm-hmm. So, and then working in science since, you've been penalised for having a family.
Well, I got married to someone who had to move to another part of the country every 5 or 10 years. And so I'd get nicely set up with an astronomy job near where he was working. And then it'd be time to move. And I'd have to go back to square one and beg for another job somewhere else. So it's not been, on paper, a very prestigious career. But I have had the chance to work in radio astronomy, millimeter, infrared, X-ray, and gamma ray, which is most of the spectrum.
Wow, that's quite amazing. But no, you've done a lot. So I was just thinking I was reading about Chandrasekhar, who figured out the white dwarf limit, beyond which a star collapses, obviously to a neutron star, and he was forced out by Eddington, who was and had to move into field after field after field because for a different reason. So it's interesting that your career has sent you into different avenues. But of course, you probably had to work harder than everyone else because you had a family, you had to prove yourself. Has that made you more determined?
I think it probably did, yes. But another way of putting it, it helps you sort out your priorities. It sure does.
So all these things have made you who you are, because I think you're quite a determined and strong person. Yeah, you are. And unlike Margaret Thatcher, who pulled up the ladder when she climbed to the top, you've done all you can to help other people in similar positions, particularly women. Can you tell me about that? You've tried to help people into physics.
Yeah, well, probably the biggest thing I've done is I won a breakthrough prize, which is $3 million. And gave it to the Institute of Physics for the UK and Ireland, saying I wanted to increase diversity amongst physics researchers. And the best place to start seemed to be with the research students, the people who've done a bachelor's degree and are then going on to do a research degree. And so the Institute of Physics, which was planning to do something similar of its own bat, put the whole lot together and have had a program running now 3 years to give scholarships to people wanting to do PhDs who are from minorities, maybe gender-wise, maybe race-wise, maybe they're not British, maybe they've got some disability, something like that. Because I thought if we increase the diversity in physics, I think we'll make more discoveries because there'll be more people feeling, oh, I'm not sure I should be here. I'm not sure I'm clever enough. I'd better work very hard. So
how many people have you helped in the last 3 years?
There were 4 in the first year. I don't personally do it. There's a committee that does the selection. They had 4 in the first year, 8 in the second year, and I think there's 9 starting this October.
Can you give me some idea of the individuals, the backgrounds of these people? Or could you give us an example of someone who's been helped?
For instance, there's a young woman who's Polish, who is studying for a physics degree in the south of England. now has her physics degree and wanted to go on and do a PhD. And they helped her with one of those scholarships.
Right. And will the scheme expand in future, or is it going to stay at this level of 3 or 4 a year?
I don't know, because personally I'm not involved. When you hand over money, you hand over money and you don't interfere. They do brief me afterwards. So I know that, currently they're running at about 8 or 9 a year. And I think they plan to continue with that, but I'm not the best person to ask.
I mean, I think it's absolutely fantastic. I mean, I'm not one of your minorities, but my parents left school when they were 15. No one in the family had ever been to university. And at my comprehensive school, I can't remember anyone even mentioning Oxford and Cambridge as even a possibility. So I'm really all for anyone who tries to help people from, I don't have a disadvantaged background like those, but I think it's just a fantastic thing, really fantastic. Good on you. So we've got some questions from some people, but I just wanted to ask you, what female physicists or scientists do you think have not got the credit that they deserve?
The one that I think deserves a lot more credit is Vera Rubin, who died a few years ago. US woman, studied the way galaxies rotate, basically discovered the stuff we call dark matter, but wasn't believed for a long time, told to go get more data, do more observations. Her data were absolutely consistent, and it was a reluctance to accept that what she was finding. Now there's a telescope named after her that will start operation very soon, and it's going to be fantastic.
That's a telescope that actually looks for darkness, really, doesn't it? It's a telescope that's looking for, paradoxically, for dark matter by the lensing of the visible stuff, isn't it? The gravity. Is that what it does?
No, it's also actually looking for things that fluctuate in brightness, and it's got a wonderful setup now. When it's going to find, numbers vary, 1 million or 10 million things that change their brightness during the night. Maybe
it will survey the entire sky in a night. Is that what it will do?
I'm not sure about that, to be absolutely honest, but it's going to find thousands of events every night. The number varies, let's say 1 million every night. And it's all got to be computerized and automated, because no number of grad students can handle that. And the computer will send out messages to all the other telescopes that it has an email address for, saying something's happening at that position in the sky now, go look.
Yeah. So things that change very rapidly, we'll get some. We'll hopefully make lots of unexpected discoveries. Really.
It's an underexplored area, so I'm looking forward to the data from that telescope.
And apart from Vera Rubin, anyone else you think has not got any female scientist who hasn't got the credit they deserve?
There's probably quite a lot. I would also put Caroline Herschel's name in the pool. Herschel's sister, who helped him with his observations, did all the writing up of the work, as well as running the house and getting meals and helping him grind mirrors and everything else that, the women do.
Yeah, my favorite is Cecilia Payne. Again, she was the first person to use the newfangled quantum theory to analyze the light coming from the sun, and she discovered that the sun appeared to be made of 98% hydrogen and helium, elements which were pretty much non-existent on the Earth. I mean, until that time, people thought the sun was made of iron, and her supervisor made her say in her PhD thesis that she was almost certainly wrong. And when, as you know, 10 years later, Henry Norris Russell, her supervisor, realized she was right. And I think he mentioned at the foot of a 158-page paper, I think it was on about page 157 or something, he mentioned her.
Oh, and, I've seen a reference near the beginning of his paper.
Yeah. And I tried to get her the credit that she deserved. And I wrote an article for New Scientist magazine about her. And when the magazine came out, I opened it, I flicked to the page, and there'd been a cock up at the printers, and they'd only printed the corner of her hat. And I thought, oh my God, and then I actually I was being interviewed at the Cheltenham Literature Festival by another Marcus, and just before we went on, he said, at the end, I want you to come up with the name of a scientist who didn't get the credit they deserve. And I thought, Cecilia Payne, I'll mention Cecilia Payne. And we got to the end and he just said, applause for Marcus. And I never got to mention her. So I wonder if she's fated never to get the credit that she actually deserves.
Well, I think she's recognised now, at least in the profession.
Yeah.
Undoubtedly. Yeah.
I'm just going to look at some of the questions that people have asked. And let's have a look. What is Jocelyn looking forward to? This is from Jim McIntyre. What is Jocelyn looking forward to most from the James Webb Space Telescope?
I don't know a lot of the science that the James Webb's going to do, but I'm sure there's going to be very interesting stuff. But I can't be more specific than that, I'm afraid.
Well, one of the things that I do know is that it could, I mean, I was talking to Abraham Loeb at Harvard, and he thinks that the telescope could pick up the infrared signature of industrial chemicals in the atmosphere of a planet around a nearby star within about 2 hours. So there is a planet around the nearest star, Proxima Centauri. It's called Proxima Centauri b. So it would be possible to determine whether there's actually an industrial civilization on that planet. It's a bit of a long shot, I think, but it's incredible what it can actually do.
And we're finding a lot of exoplanets now, planets around other stars. That's a very big field of research these days.
I mean, now I think it's more than 4,000, isn't it? 4,000.
I suspect it is, yes.
It's pretty incredible. But I think what the James Webb can do is actually see the infrared fingerprints of biomolecules, you know, things like oxygen, methane, things that we would expect life to generate. That's in the special case where the planet is orbiting in the plane, you know, so it comes between us and the star, so the starlight shines through its atmosphere and we can see the bites taken out by the atmospheric gases. So that's very exciting. And of course, it's finding the most distant galaxies we've ever seen. Are you excited about that?
Yes, I'm following that a bit, but there's a lot of things to follow in the world.
Yeah. Someone thinks that cosmic nucleosynthesis sounds like a Pink Floyd track. That's someone called Hashbury Stumble, which is an odd thing to say. But
cosmic nucleosynthesis means that many of the atoms that are in our bodies were actually fabricated in or around stars. So we're children of the stars.
I find this the most extraordinary thing because it makes me think that the astrologers weren't courageous enough. You know, they thought that our future is predicted by the stars, but in fact, we're much more intimately connected to the stars than that. You know, you want to see a piece of a star, hold up your hand. You know that you're stardust made flesh. You know, you were literally made in heaven, which I find pretty amazing. You know, I mean, and I think recently. You'll know about this in 2017, we picked up gravitational waves from a neutron star merger. So the merger of two of the kind of stars that you discovered. And we saw that from the gamma rays that were produced, that something like 10 times the mass of the Earth was converted into gold in that merger. And we've long wondered where gold was made. I mean, so, you know, if you've got a gold ring or a gold necklace, those gold atoms were forged by a merger, a collision of two neutron stars that happened before the sun and the earth were born. I mean, can there be any more amazing illustration of the connection, you know, between the very close and close to home and the far away and the cosmic? I mean, I think that's quite amazing, isn't it, really? As you say, we are children of the stars, aren't we?
Yeah, the atoms in our body, other than the hydrogen, were all made by stars or collisions of stars.
Yeah, and of course we talked about Fred Hoyle, and the reason he should have got the Nobel Prize was because of a paper in 1957 named after the Burbage, Fowler, Hoyle, the two Burbages, Fowler and Hoyle, V squared FH.
squared.
That's right, after their initials, and where they basically laid out at the time, I think about 8 processes that went on inside stars that made the majority of the elements.
Yeah.
And that was an incredible thing. And I thought we were
They
talking about
make the majority of the light elements. We need explosions and collisions to make the heavier elements.
That's right. So the light element, so really, yeah, the lightest elements were made in the first 10 minutes of the Big Bang, weren't they? And I mean, we're going back to Nobel Prizes here. I know that the fact that Willie Fowler got the Nobel Prize and not his friend and colleague Fred Hoyle did drive a wedge between them for the rest of their life, because obviously Fowler knew that he should have shared the prize with Hoyle, so that was a problem for their friendship.
That's a shame.
It is a terrible shame, isn't it? What happens? I'm looking at other questions. Someone says over 4,500 exoplanets have been confirmed already.
Yeah.
So that's pretty incredible, because I mean, before about 1995, we had no evidence whatsoever of any planet around any star. And I suppose the most surprising thing is that the planetary systems we found are so incredibly different from ours. And ours does not appear to be a typical solar system.
Indeed, there's one pair of stars that have planets going around the pair. So there's 2 suns in the sky for that planet.
So do the planets go around both together, or do they go on a figure of 8 between them?
No, I think they go round the 2 together.
Yeah,
if I remember rightly. Yeah.
Yeah, and certainly most stars in the galaxy, most stars are binary stars. I mean, our sun is a bit unusual, isn't it? In just having,
Yeah.
But yeah, you're absolutely right. I mean, that must be incredible to see 2 suns rise one after the other in your sky. There's some pretty amazing things out there.
Yeah.
Let's have a look. Any other questions from people? Is there a place for a novice conjecture in science, i.e. outside the box thinking? What do you think? I think you have to absorb a lot of science and a lot of maths before you can actually do anything. I don't think it's possible. I mean, you probably get this, Jocelyn, but I constantly get people emailing my website saying, I've got a new theory of the universe which shows Einstein's wrong.
Yeah.
It's 2,000 pages long. Can I send it to you?
Yes. I know the phenomenon.
Yeah. But I mean, it's really practically difficult for somebody outside of science to contribute, isn't it?
Yes, you really have to know a lot of science yourself before you can start making a sensible input or asking sensible questions.
Yeah, it really is very hard. And
so don't do physics degrees, everybody.
Yeah, and certainly things like particle physics, you'd really have no hope whatsoever without absorbing quite a lot.
I think that's true of any field, isn't it, these days?
Yeah. So, I mean, I suppose really Fred Hoyle came from a generation when it was possible to, contribute to lots of fields, really, but that's kind of gone now, hasn't it? But do you think that because science has become very compartmentalized, because it's inevitable that it is, that there aren't that people with the overview who might be able to, who can... I remember Hoyle was able to move from field to field. I remember that after the Second World War, he realized that there was a lot of nuclear data that was being declassified, and therefore it might be possible to make progress in understanding the nuclear reactions that went on inside stars. And then when he exhausted that field, he would kind of fly upwards like a bird above the scientific landscape and try and find somewhere else that he can contribute. Are there many people that can do that, do you think?
There are people who can shift from field to field. Is too strong a step, from one part of a field to another part of a field, and do good work in that. But I've moved a lot, worked in lots of different wavelengths. You need quite a considerable startup period while you learn the new field before you can really do something sensible. So a year or two to learn a field
Well,
even
there's
as
someone here says he's just working on his theory of quantum gravity. That's Jim McIntyre. Well,
right. Look,
good luck. Good luck with that. Someone
yeah.
says, is the Drake equation a valid one for the existence of life in our galaxy?
It's got the right sort of ingredients in it. Yes, it has. How much weight you give to the different ingredients is another question. That I think is still debatable. And the Drake equation was formulated when we were unaware of the complexity of other planetary systems. You know, we've already talked about one planet orbiting a pair of stars. There's greater variety around than we had originally thought. And the Drake equation works on the assumption that there's a single star with a single planet, and over there, another single star with a single planet.
Right. Now, the producer of this program, Kevin, would like to know why you are the Chancellor of the University of Dundee.
It's a grand title. Chancellor is the person who presides at degree ceremonies. So in Dundee, my job is to sit on a sort of throne and tap all the graduates on the head with a cap. We did 3 years worth of graduations this summer. It was a marathon, but it's a very joyful occasion. So it's real fun to do. And I'm coming near the end of my term there, but it's been really nice to be in on the celebrations at the end of a degree.
Right. So looking back over your career, what are you most proud of?
Surviving, I think, probably. But I've had a huge amount of fun. I've worked in radio astronomy, infrared astronomy, millimeter wave astronomy, X-ray astronomy, gamma ray astronomy, and had real fun in all of them. Superbly varied and very, very interesting. So
Is that unusual to go between all these? It's very unusual to go between all these fields.
It's because I was following my husband around the country as he went from job to job to job. They were often very lowly jobs, but I had a huge amount of fun and learned a lot.
And in each job, you had to spend quite a bit of time getting up to speed on the new field.
That's right. Yes. Yeah. And sometimes I'm working with balloons. Sometimes I'm working with satellites. Sometimes I'm working with a telescope on Mauna Kea. You know, huge variety in that sense as well.
Yeah. So you've really enjoyed your career, even though they didn't give you the Nobel Prize.
Indeed, very much enjoyed it. Probably because they didn't give me the Nobel Prize.
Yeah, well, I mean, I remember I was very fortunate to be taught by Richard Feynman when I was at Caltech, and he did dabble with the idea of turning down the Nobel Prize because he thought that he would end up on committees and he wouldn't be able to do any basic research anymore. But then he realized that if he turned it down, that would be an even bigger, that would make him even more famous. And so he didn't actually turn it down. But he did manage to avoid being on any committees, and I suppose people thought he was a bit selfish, but that was the way he was able to continue doing work. So it can be the Nobel Prize can be a curse, I imagine.
Yeah, it
I mean,
can.
of course, there's the people that didn't get it. I'm thinking of like Max Born, all of his students, you know, Heisenberg and Pauli and all these people. They all got the prize, and he never got it until he was about 80 or 85 or something like that.
Yeah, yeah.
So that I think that probably there was a lifetime of feeling that he'd been overlooked. So it's a weird thing, isn't it? The Nobel Prize.
It is weird, yes.
And also, I suppose it doesn't actually reflect the way that science is actually done. I mean, it's done mostly by groups of scientists. You know, there's very few lone scientists who make discoveries now. I mean, I'm thinking the gravitational wave work, probably several thousand people involved. You know, I mean, maybe we need a prize for a team rather than an individual now.
That's beginning to come. Some of the professional bodies are now certainly thinking about, and I think maybe one or two have actually taken the plunge, having a prize for a group of people, a team of people who've made a major discovery.
Because, I mean, if you take the James Webb, I imagine there would have been thousands of people involved in building the James Webb telescope. And of course, the project scientist John Mather got the Nobel Prize for COBE, the satellite which looked at the afterglow of the Big Bang. And again, there would have been a team of about 1,000 people, and they only gave it to 2. And so it gives people, I think it gives the public the wrong impression of how science is done these days. I mean, science is just big science everywhere. All the low-hanging fruit were long ago plucked, I think, by the likes of Isaac Newton and all these people.
Yeah, and that also says scientists today have to be able to work in teams. You have to get on with other people. You have to negotiate and compromise and so on. Yeah.
So you need a lot more skills, which brings us back to Neil Turek, who you were speaking with in Ghana, because I mean he is an extremely unusual physicist who he's good at organizing and running groups of people, like the Perimeter Institute in Ontario, as well as being a front-rank cosmologist. You know, that's a really unusual skill to have. To have those 2 skills.
Yeah.
Anyway, well, thank you so much for talking to us, Jocelyn. It's been absolutely fascinating. I'm really it's been a real pleasure to talk to you, one of my heroes.
Thank you.
That's fantastic. And I'll be back in a month's time to do this all over again. And I'll be talking to Feryal Özel, who is the Turkish-American astrophysicist from the University of Arizona, who was one of the key people in creating the recent image of the supermassive black hole at the center of our galaxy. So until then, thanks for listening, and goodbye.
Bye-bye. Thank you. Bye-bye.